There's no plant.
I've never heard of a plant being in that hallway.
Never heard of it,
Never saw one.
never saw Cormac with plant.
I never saw one with a white base either.
Nope,
Nope.
absolutely.
Never.
That plant needs water like stat.
It's a Dieffenbachia, a kind of peace lily.
Ooh, nice.
Mom's a florist, so I texted her.
Oh, didn't you? That's
Yeah,
awesome.
we keep this alive.
How can you not have any plants when your mom's a florist?
She just started her floristy.
Oh, neat.
side.
Oh, that's cool. That's a cool adventure in life.
Yeah, I have a lot of plants at home.
Okay,
Just not here.
just not here. Got it. Is there anything you all have? Yeah, let's see. We have an assignment due on Wednesday. I'm going to try to get these back to you. But what's that? It's up in world class. Can somebody bring up world class? I think you had trouble finding the first one too, right?
This one for real, I love it.
Okay, all right.
I see it. For real, for real.
It was 3. No one said anything to me about this so far, so I'm assuming no one has started
No.
the non-existent problem. So go to the, and then, no, oh.
Yeah,
There's just.
the world class is like kind of.
The fuck? Wait, okay, can you go back to the calendar? Look at this,
I like the due
what's
date
going on
thing.
with the plant? There it is.
Let's see.
What?
Mine has it.
Where?
It's right there.
Where did that come from?
Nice.
But like, where is that?
Like it's not in the.
It's just, you just go, like,
Always
look at this, bro.
No, 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 but like, look.
Okay, go to the book. Go to the book.
I'm going to the book.
Now look at section 2, go to not sage exercise. Yeah, there you go. There you are.
Well, yeah, but like, I don't know which ones you wanted us to do.
Well, they were listed in that thing.
Well, yeah, no, I'm saying I had no idea where
Oh,
to find
okay.
that thing. Like,
Okay.
that's the only place that has since shown up.
So how about you get these to me by Friday, and then if there's like in the future, when I give you a homework assignment, which I will on Wednesday, if you're like, I don't know where that is, we talk about it sooner.
Yeah.
Yeah.
Sooner. So let's see. So let's see. The 3 homework problems were, what are they?
2, 4, and 6.
2, 4. What were they? I'm sorry.
2.2, like
2, 2.
second before the
2,
first.
and then 2, 2, 4, and 6.
Okay. Thank you.
Yeah.
3 induction problems.
Wait, I see 2.4.2,
Mhm.
2.4.4,
Yes,
and
yeah.
2.4.6. Yeah. Sweet.
Yes. I'm glad we had this talk.
Wait, okay, I read that up there as like 2.2.2 and then question 4 and question 6.
Why are you doing this to me?
I'm sorry, I'm really slow today. I'm having a hard time.
Just really being a miscreant today.
I'm just having a hard time today.
It's been a long summer.
It's been a really long day.
It has. Why don't we just take a day off? No, it's not today. That'd be a waste. No days off yet. We already had this conversation. I know, sorry. Camila's really hoping it was. We'll take a damn day off, but not yet. Okay. Are there any other questions? Like, where's the book? Or, no? Oh, good, we're good. All right, cool.
Ready.
What do you mean algebra? All right, so today we've got a pretty interesting thing. At one point in my life, I didn't really realize how awesome this is. The division algorithm. How many folks have seen this at some point? Probably in like, if you've looked ahead in the book for sure, but logic and proof? Yeah, should do some stuff with it. Okay, cool. So this was Euclid. Euclid came up with this. So, you know, literally one of the first like school things ever created. Euclid wrote the first textbook ever. It was a math book called The Elements, which you maybe know if you did history of math or something like that. But the division algorithm says this, that if I have 2 integers, a and b, and one of them is positive, essentially what we're going to do is we're going to divide b into a. But it looks weird. So this is like division like you've never seen it. That if this is true, then let's see, for all, then we can write A equals some multiple of B, and I'm gonna put Q for quotient, plus a remainder. So in other words, if I want to divide B into A, B goes in a certain number of whole times and there's a little bit left over. Now, we have to have this particular caveat on the remainder. So the remainder is less than the thing I'm trying to divide into. If it wasn't, I didn't get the full amount of full multiples of this thing that went in there. And this Q and this R are unique. And they're only unique because of this restriction right here. But there's only one way to do this, provided that remainder is less than the divisor. So let's look at some examples. And let me show you some graphical ways to think about this. So for example, if A is 15 and B is 7, I'm going to take 15 and figure out how many whole multiples of 7 go in there. So that's 2 times 7. That gives me 14 plus 1. No, not profound, right? Not really weird at all. What about, and actually here, let's kind of take a look at the picture. Oh, just a number line. So on the number line, if this is 0 and this is 15, what I'm doing is I'm taking a stick of length 7 and I'm measuring this way. So here is 7, here's 14. So I'm kind of just laying these whole things out. The Greeks were all about measurement. This all came from just measuring sticks, and then there's my little remainder. Let's look at a different one. What if I have A is negative 15 and B is 7? So this is going to change some things. Let's take a look here. So here's 0 and negative 15 now sits over here. So I'm going to find out how many whole multiples of 7 go in here. So this takes me to minus 7, minus 14, so there's 1, 2. Now look at the remainder. The remainder has to be non-negative. So I'm not going to say the remainder is minus 1. I have to actually go another full multiple to minus 21 because the remainder is always non-negative. So that means I go to minus 21, so in other words, minus 15 equals minus 3 times 7 plus what? What gets me back? 6. And notice that that 6 is definitely less than the thing I'm dividing by. But the remainder is always a move to the right, to the positive direction. That's how to remember that. So this can confuse people pretty often. That's why I just wanted to get it up there right away. And there's really not much more to say about it. Now let me give you one just to try. Could you do this one for me, please? Could you apply the division algorithm? So this is called dividing when I write that equality out. Could you divide minus 31 by 7? So we got another 7 in there. What's the minus 31 do?
Negative 5 times 7 plus 4.
Go to minus 35, back up 4 units, perfect. Just looking good to everyone? Let me stop for a second. Make sure, everybody make sure you get that in your head and that it makes sense to you. Good, Penelope? Camilla, you feeling okay on that? Okay, awesome. All right, so this is what we're gonna mess with today, but I want to take a slight digression and then bring these two things back together. So we're gonna come back to this, but first I wanna talk about something you're very familiar with, common divisors. But before we do that, I wanna talk about the fundamental theorem, that sounds important, of arithmetic, for Christ's sake. Sorry, Christ. Or folks who might be offended by that. Let's see, I'm just making sure I'm recording here. Okay, cool. So, fundamental theorem of arithmetic, that sounds really primal. Does anybody know what it is? It's weird, right? It's like arithmetic. It says this: for every n that's a natural number, so 1, 2, 3, 4, 5, on up, just the nice whole numbers, I can write n as a product of primes raised to powers. So this is the prime decomposition, the prime factorization of this number n. So it's equal to p1 to some e1, p2 to some e2, dot, 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 p sub n to the e sub n, where p sub I is a prime, e sub I is greater than, and e sub I is greater than 0. Otherwise, I wouldn't write it down if the exponent was just 0. There's a couple ways to formulate this. This is what we're going with. And to make sure that this is a unique factorization, these primes are in increasing order. So this right here ensures uniqueness. Otherwise, you could switch the order around, but we don't want to make that a different factorization. So yeah, just make a little note here, prime factorization. That's all it is. And every integer can be uniquely written as a product of powers and primes. So let's take a look at some numbers and their prime factorization. So how about 102? Have you ever heard of the sieve of Eratosthenes? Yeah, it's like a way to get prime factorizations. So what you do is you start dividing through here by primes. What's one thing this is definitely divisible by?
2.
2. What's actually another thing? That's right, 2.
51.
Yeah, you got it, yeah. That's what first I thought that, but what's, yes? What's
It's divisible
1?
by 1.
Definitely, yes. What else is it divisible by?
0?
No,
No.
Lordy. No, nothing's
I don't
divisible
think
by
so.
0.
102.
Yes, 102. 1, 102.
3.
Minus 102. 3. How'd you get 3?
I did, 99 and then plus 3 is 102. And I know 99.
That's interesting. So the digits add up to what?
3.
3. Anytime the digits add up to a multiple of 3, it's divisible by 3. So that's a good test. It's even because it ends in an even number, right? So I know it's divisible by 2, so I'll go through here and do the division by 2. And this Abraham, this was literally how I came up with it. I was like, well, let's do 50. Nah, let's do 2 times 51. This digits add up to 6, so it's divisible by 3. And this is literally one of my favorite facts, that 51 is 3 times 17. I don't know why, but I like it. It's cool. It's weird. It's weird. It's unexpected. So 17 is prime, so I just say 102 equals 2 times 3 times 17. Yeah. And I got the prime factorization. We could do this, right? and it can get worse. So let's assume we've done it. Let's assume that A is 2 cubed times 3 times, I'm gonna put the things in here that I don't have an actual positive power of, but it'll help with what we're about to do, times 7 to the 0 times 11 to the 5th times 13 squared. And we don't want it, that's a big ass number. And then B is going to equal 2 to the 1st times 3 cubed times 5 to the 1st times 7 to the 0 times 11 times 13 to the 0 times 15, no, not 15, what's the next one, 17? I think that's the next part. 17 squared, sure, did that. So, someone has done a painful job for us, right? We're coming at the painful job from the problem maker's side of it. So the question here is find the greatest common divisor of A and B. So what we're looking for is i.e., and let's put this up because it's actually important that we understand the definition of this. Some D that's an integer such that D divides A, D divides B, and D is the biggest number to do those things. And we're going to talk about how to say that mathematically. D is the largest such divisor. Let me let you get caught up with that. This is actually a totally kind of different way. It's just happening than I thought it would, but this will be great. Everybody. So I've got to find the greatest common divisor of A and B. It divides both numbers, and it's the largest such divisor. What this means, i.e., is that if D prime is any divisor of A and B, so i.e., if I have D prime divides A and D prime divides B, then this divisor has to divide this guy because he's the biggest. Then D prime divides D, and that's the way we mean biggest. So D is the biggest. Very subtle. Do you see how the definition rolls? That any other divisor divides the greatest divisor. So, once I have a factorization, this is an easy job. Can someone maybe talk us through how to find the GCD of these two numbers? I want a number that divides both these, and it's the biggest one. So let's say here D equals GCD of A and B. What power of 2 should I use?
2 squared.
Does 2 squared divide this guy?
Oh, there's 2 then.
Just 2 to the first. So I'm going to pick 2 to the first because that's the lowest power that's in common to both of them. What power of 3?
Just 3 first.
3 to the first. You see how this is rolling? What power of 5? 0, so not even a 5, right? Don't even put that in. Can you finish this up for me?
Do you need to put the powers of 0 in there?
No, not at all. I'm just putting them in for us to kind of like have placeholders, but absolutely not, Abraham. Yeah, so like 17 to the 0, I'm not going to put that in. So in fact, it's just 2 times 3 times 11, looks like a good old 66 is my greatest common divisor. Does that sound okay? So that's one way to get the greatest common divisor. Once you have basically the x-ray of the numbers, you can go through and just pluck what you need out of there. Let's talk about one other important thing that we will be using often when we start doing algebra, which is this week, by the way. We're actually making the move this week, the big leap this week. The least common multiple of A and B is the smallest number that's divisible by both these things. Equals the smallest integer, we'll call it L, such that A divides L and B divides L. That's called the LCM of A comma B. And then this guy over here, I don't know if I wrote it, this should be the GCD, so you write GCD of A comma B, greatest common divisor. This is the LCM. So now let's look at these factorizations over here and think about how we're going to do this. I want a number that is divisible by both these numbers, not the number that goes into both of them. And I want the smallest one. So what power of 2 would work if I want both these numbers to divide it? 2 cubed. I could go to 2 to the 4th. I'm going to go through each of these, by the way. It's not just 2 cubed. But if I go through these pairings, I'm always going to pick the largest. So it's the opposite of what we just did. So LCM here is 2 cubed. Pick the highest power. Can you finish that up for me, please? And then we'll take a look at a result that we're not going to prove, but we can intuit. And I don't know what, these are going to be big ass numbers, so we're not going to, unless you're like feeling super spicy and want to crank them out for us. Does this look good? Literally just went through, grabbed the highest power in the factorization. Cool. So now look at something here. What is the least common multiple? So first off, does this make sense? We see how to do this. These are chill, right? Like we hope our problems. This isn't going to be your homework. This is too chill. The least common multiple of A times B, or A comma B, times the GCD of A comma B. Wow, what a weird thing to think about. But let's go through and think about what each of these involves. So the GCD is pick the lowest power that appears. The LCM is pick the highest. So when I go through here, when I do the GCD, I'm going to pick all the low powers and multiply them together. And when I do the LCM, I'm going to pick all the high powers.
So it's freaking everything?
It's freaking everything. And what is it actually equal to? A times B. It's just everything. So it's literally equal to A times B. And that's a really good result. And let me tell you why it's a really good result. Because this is we're gonna have an algorithm for this that has nothing to do with the factorization. But we can use that then to find the LCM. So the LCM of two integers is going to be the product of those integers over the GCD. So you can divide the greatest common divisor out of the product and get the LCM, which is cool. Now we're gonna have fun, because this shit is so weird. What's about to happen, like, I don't know why. I've literally spent hours this weekend trying to come up with a way to explain to you why this works. Like a good intuitive way. So that you have a picture. I don't have that yet, but I know it works. So good old Euclid. Let's go visit Euclid again. There's a thing called the Euclidean algorithm, which you may have had in logic and proof, the Euclidean algorithm to find the GCD. Well,
Sounds familiar.
there's you know how logic works, so if you had MT401, then I can assume certain things. So remember that if this is false, that statement is still true. I'm just saying logic. So, let's talk about the Euclidean algorithm. for finding the GCD of A and B. And it's all about the division algorithm, recursively applied. So plan recursively, if you're a CS person, that word is near and dear to your heart, or your horror, or whatever, both. Recursively apply the division algorithm. Now there actually is a proof of the division algorithm that I'm not doing, but it's in the book. Enjoy. I'm gonna do a proof that's similar to it. It's not a fun proof. I mean, proving anything Euclid did is not fun. Just a rule of thumb. Recursively apply the division algorithm. So, I'm going to show you the general plan. So find the GCD of A comma B, and let's assume that B is bigger than A. You're just gonna pick the one that's bigger. It might not be the second one, but just assume, what do I mean by that? WLOG, what's that mean? We love our grapes.
Sounds like something that a work would say, on like a game or something.
Long, like that, yeah. No, without loss of generality. That's a good mathy thing to know. So without loss of generality. One of those two things is going to be big. If they're the same damn number, we can't, doesn't even, problem doesn't make sense. Generality. Just assume B is the bigger one. So what I'm going to do is I'm going to use the division algorithm, so divide A into B. And what I mean by that is write this. B is equal to some multiple of A plus a remainder. And that remainder, of course, is less than the smaller of those two numbers. Here's the plan. Now, I'm going to do that. We've already practiced that. Now I'm going to take this A, the thing I'm dividing into, put it on the right. I'm going to take this remainder and divide this remainder into A. So how many times does that remainder go into A? And we'll just call that Q prime right here. And there is going to be a new remainder, R prime. We just have to figure that out. Now I'm going to take this setup and I'm going to shift it again. So I'm going to take this remainder here and move it here. And it's equal to however many multiples of that previous remainder, we'll call it Q double prime, plus R double prime. So notice how I'm taking these two things and just shifting them through the division algorithm. And the part you have to figure out each time is how many multiples and what's left over. And then that moves to the next line. So we will continue this till eventually what's going to happen is you're going to get eventually the remainder will be 0. And you're done. And I'll show you what to do with an example. So you keep doing this until you get a perfect division. There's no remainders, and I'll show you what to grab after that. So let's do an example. I've got some weird numbers I wrote down. Yeah, here's a good one. Find the GCD of 101,400 and 994,500. Big ass numbers. So let's do this one together. Bigger of the two numbers is that guy. So I'm going to write 994,500 equals, and I'm going to put this guy here. How many times does that go into here? I think 9, right? If we do 9 times, this will be 900,000, and then this part won't be more than the 90 right here. So we've got 9 of those. We definitely can't do 10 of them because that's bigger. So I've got 9 of these, and then what's left over after I pull out 9 of those? Can you tell me when you find out? I've got it written in my notes, but. Thank you, 81,000, and I remember that, indeed, thank you. So that's step 1, the remainder is not 0, so I'm not done. Now I take this, make this the left-hand side, 101,400 equals, and then I'm gonna put this guy here, 81,900, and how many times does that go into here?
Once.
Just once, yeah, just once. And then just find out what's left over. I gotta subtract, and if someone could do that for me, that'd be so peachy. Christian, wait, Cormac, do you guys remember when I said peachy in Calc 3 and people lost their minds? They didn't even, yeah, that was weird. Weird. You were in there too, Camila. You remember that? Yes. What was wrong with those guys? Yeah, a lot. I mean, a lot.
19,500.
That's it. Thank you. 19,500. Can you finish this up for me until you get to 0? Oh, I got great faith in you, Abraham. Is it 4? Is it? Yeah, okay, cool. Probably should be just about done. And I think it's 5, right? And done. And let everybody get caught up, because we have our GCD. This is it right here. That's your greatest common divisor. So GCD is that number that's the remainder right before you get a 0 divisor, or it's the thing that cleanly goes in to the thing on the left. But the GCD now is 3,100. And that's cool. I just think that's cool. It's just sifting it. You're breaking apart remainders and dividing them. And Euclid was pretty amazing. See, it's easy to think this looks easy, but when you're like sitting under a palm tree in the sand, you know, and you come up with this, that's pretty awesome. Is there any questions on that method? So how do I find the least common multiple of those two god-awful numbers? I multiply them together, divide by 3,900. So the LCM, and we don't care what the answer is. We're just gonna write it out. It's 101,400 times 994,500 divided by 3,900. Cool. That's a lot of cool work done with just like rolling through it. And like I said, I don't have a good way to explain why this works to you yet. I hope to by the end of the semester. I don't know, I'll probably forget about it after we leave class here today. But if anyone comes up with like an intuitive way to understand this, I would love to hear it. I watched a bunch of videos, none of them helped at all. It's just, I'm not feeling it, but I know it works. So, that is a very important algorithm. Let's do one more. Oh, why not? Oh, why not? Because it's fun. And this one I already did. I want to just try this one here together. Let's do 234 and 165. Look, I don't know the answer, but it sounds soothing to try to find out.
Is it that you always put the bigger number on the left side?
Yes, yes. Was 69 the remainder on the first one?
Mhm.
Cool. Okay, awesome. That's like 70, so 2 of those. And then that's 138, 165, 27?
Yeah.
Yeah, cool, cool. 69 equals, I think just 2 of those, right? 3 of them goes too much.
Yeah.
Mm-hmm.
Yeah, so 2 times 20. That's 54. How much?
15.
15, thank you. And then 27. Wow, this one's cool. This one really goes down. 1 times 15 plus 12.
Mm-hmm.
Wow, I love it. 15 equals, we gotta be there. 1 times 12 plus 3. That's our buddy, isn't it? 12 equals 3 times 4 plus 0. So that's our greatest common divisor. Cool. Neat. That's quite a sieve. Quite an amazing process. So, occasionally we'll need that. This is just more like, oh, did you know? And won't it be cool if you ever have to find the GCD of some things? In general, that will not be something we do in this class unless it's just like a problem to find GCDs. What we will be doing is the following. So we have a theorem. I am going to prove this. And this theorem will become vital to our work. If the GCD, oh wait, let me just make sure I got the phrasing right here. Yep. GCD of A and B equals D, so I'm just labeling it with that. Then there exist unique. So this notation here, that exclamation point implies uniqueness. So this is an existential uniqueness quantifier. There exist unique integers S and T. So there's only one way to do what we're about to do, such that D is equal to S times A plus T times B. That you can express the greatest common divisor of 2 integers as a unique linear combination of those 2 integers. And I'm going to write that in words. So the GCD of 2 integers, because I think that knowing this in your head is a good thing. The GCD of 2 integers is can be expressed as as a unique linear combination of those integers. So I'm sorry, my handwriting started just decomposing as I wrote that. Apologies. Sometimes I start writing stuff and I just get bored. Like, it's just like, oh God, I just want to get through it. That's not helpful to you. So I want to prove this because it's cool proof. It's kind of an amazing fact. It doesn't seem intuitive at all. Like, why would this be true? So let's do the proof. We're going to define a set S. So let S, that's a big Gothic S, that's why I'm putting fancy bars on it. Let S be the set of, so we've got these two integers A and B, right? We've already got A and B. Let's actually put that in here. A and B, we've got those guys. I'm going to define the set S that is S times A plus T times B. I'm going to let S and T run over all the integers, but I'm going to require that whatever integers we choose, they have to leave this thing positive. So I have a question for you, and I need someone to tell me this. This set is not empty. Why? And let's say that A and B are not, neither one of these are 0. So I'm going to subtract off 0 from the integers, so neither of these guys are 0. That's all I'm trying to say. Can somebody tell me why that set's not empty? No matter what A and B are. And pick a couple to see why. Why do I know I can always find some? Cormac, you got some? You look like you got some.
Well, aren't you just saying like all S and T in the integers applied to S times A plus T times B?
Yes.
It's like there has to be something in it.
See, like what? So tell me more. Yeah, you're right.
Like,
It does.
If S and T are 1 and 1, I guess.
Well, what if A is -2 and B is -7?
Then you just pick 2 negative integers.
Just pick the freaking integer that makes the thing positive. Yeah. So no matter what A and B are, you could pick a negative number to put it in front to make this positive. You could pick a 0 for one of them, right? So you could just kill off one of them and pick whatever multiple makes this thing positive over here. So this is non-empty. So that's important. So S is non-empty. We'll say clear to reader or something irritating like that. I do the math bullshit. Like, obviously, this set is not empty. What does the well-ordering principle say?
There needs to be a smallest element.
Ooh, yeah, I like it. There's someone who's read. Thank you, sir. The well-ordering principle. Do you know what the well-ordering principle says in general, Christian? Like how you would state it?
No.
That's okay. Does anybody know the well-ordering principle statement?
There exists some element in S such that for all other S it's smaller than M. Is that somewhere along those lines?
It's more of a statement about the naturals and subsets of them, not necessarily this S.
Yeah.
Well-ordering principle. We're close. We're close here. I don't know if we're close with I don't know, but we're, by the well-ordering principle, i.e. every non-empty, when I say it, you'll say like that seems obvious. Empty subset of the naturals has a least element. That's not true of every set. It's only true of the naturals because they are discrete and they are countable. But it doesn't always have to be true. For example, the rationals, if we had real analysis at one point in our lives, we would know that not every subset of the rationals has a least element in it. How about that set? It doesn't even have a 0 in it, right? That's an open interval. So this is a very particular property of the natural numbers. But that's a subset of the naturals because everything in it is non-negative, right? All the SA plus TB stuff, that's a natural, each one of those is a natural number. At a minimum, you know, you've got 0. Nothing can get less than 1. These are the possible things in that set. So any subset of that set has a least element. Proving this is a horrible, horrible thing to see. And I leave that for you to enjoy. By the well-ordering principle, there's a least thing in S. S has a least element. And let's call it D. That least element is the greatest common divisor of A and B, and we're going to prove that. So we create this set, we pick the smallest thing in it, turns out it's the GCD of A and B, and that's what we prove. And that seems amazing. Claim, subclaim, D equals the GCD. So we're going to prove this using the division algorithm. To show this, divide A by D. This D, that least element in there, I'm going to divide that into A. So in other words, i.e., write A equals some quotient, some number of D's that go in there, plus some remainder. And that remainder is less than D, possibly 0, but I'm just writing down the division algorithm here. So let me stop and you tell me if this makes sense, because I'm just writing down. Yes, sir?
If D is the greatest common divisor, isn't R going to be 0?
It is, but we don't know that yet.
Okay.
You're right, absolutely. So yeah, so Cormac's saying, well, wait, if D divides A, R has to be 0, and we're going to prove that R has to be 0. So yeah, you're totally on spot with that. So what we're going to do is say, all right, let's divide this thing into A. That better be 0. So what we're going to do is say, what if it isn't 0? So we want to show that R is equal to 0. So assume it's not. Assume R is actually positive. But remember, R is still less than D, right? Still less than D by the division algorithm. So we're going to assume R is positive. So take this thing here and rewrite it. It says that R equals A minus QD. So I just took this division algorithm thing, rewrote it. I'm assuming that this thing is positive. My voice is changing. I'm assuming that. Well, this is a why is that? That is positive. Okay, hold on. Shit, I lost my way. Because now I'm like, what? How can this possibly be? Oh, yes. Okay, cool. Yeah, okay, I got freaked out for a minute. Because I was like, wait a minute, and this has to come back to that set S. And the link is that I already know D is in this set, so D looks like this for some numbers. So, sorry, let me pull, I was kind of talking to myself there. But D is an element of S. We already assumed that. So, D equals S times A plus T times B for some S and T. There we go. Because it's in D, or it's in that set S. So I'm going to rewrite this. Therefore, R is equal to A minus SA plus TB times D, or to Q, thank you, times Q. So I'm replacing that D with this expression, and that's positive. Now let's play with this. This rewrites as A times 1 minus S Q. So I'm pulling this term together with the A, plus B minus B, I'll put plus, B times minus TQ has to be positive. Let me stop. Do you see where I got that? I did a little funky algebra here on this expression, and I grouped together the A stuff and the B stuff. So see, check me out on the algebra, make sure it's legit, please. And if do you want me to go through it? Just say yes. Just like hold a thumb up or something. So. Just to make sure, because I see people thinking about that. So I'm going to take that left side, that's A minus SAQ minus minus TBQ. That's that left side. So I just grouped these guys together, and that became this, and then this guy's just right here. Let me stop. I see people still thinking. Because we're almost done once we see that. How do you feel about that, Sophie?
Feel good.
Oh, sweet. Okay, cool. So this R, this thing here, looks like this. That means that R must be in this set. So this thing here, right? I've got some integer times A plus another integer times B, and it's positive. That's everything that's in S. So this thing here, so R is an element of S. The remainder must be a number that's in that set over there. But R, well, we're assuming R is positive here, and it's less than D. What is the contradiction?
We said R has to be zero.
You have to say it again.
We said R has to be greater than zero.
D was the least, the smallest one, and it can't be less.
Yes, yes, so D is supposed to be the smallest thing in there,
R.
and we just produce something smaller in there.
Mhm.
So does everybody see that? The contradiction is that I have just created, if R is positive, then R has to be smaller than D, but that contradicts the fact that D is the smallest. So this contradicts, see exclamation point, the assumption that D is the smallest thing in S. Christian, you good? You cool? Okay, cool. I saw you deeply considering this. So what created that problem? What's the contradiction stem from?
R not equal to 0.
That R must be 0. So all this trouble arose because this thing ended up being in that set because we assumed R was positive, so R must be 0. If R is 0, then we don't have to worry about that thing being in the set and being smaller. So we come here now and we say, all right, well, R is equal to 0. So R must be 0. And R is 0 means what? That D times Q is A. Therefore, A equals DQ. And D divides A. There's no remainder when I do that division. Because if there is, we have a contradiction. So now, notice that this whole argument, I could replace A with B and the same thing rolls through. I could have used A or B here. So I'm going to say, without loss of generality, or similarly, we can show that D divides B. So that least element divides both A and B. That's cool. What do I still need to show? That it's the greatest thing that divides both A and B. So now let's summarize where we're at. Now we know that D, which is that minimum element, D divides A and B. Cool. We're going to show it's the greatest, and this is pretty slick and quick. Need to show NTS. That's my need to show that D is the largest of the divisors. Of A and B. So what we're going to do is we're going to assume we have a different divisor and show that it has to divide this D. So plan, and I wouldn't write all these plans up normally, but it helps us think through what's coming in the proof. Plan, assume D prime divides A and D prime divides B, and show that D prime must divide D as well. So Cormac, what we're going to do, just real quick, we've got that D divides A and D divides B. We're going to show it's the greatest of those divisors now. So I'm going to assume that I have a different divisor of A and B. So assume that D prime divides A and D prime divides B. Well, then you write out what that means, i.e. A equals some multiple of D prime. So I'm going to say K times D prime, and B is some multiple of D prime as well. It's not necessarily the same, so I'll put an L D prime. I'm just writing that out, taking the definition of divide and writing it out for some K and L that are integers. But we know how we got D. D is equal to AS plus BT for some S and T. We already know that. So now I'm going to plug in those definitions of A and B that I just put these breakdowns here. So this implies from down here, A is equal to K D prime times S, and B is equal to L D prime times T. So look, D prime can be factored out. And so I have D equals some multiple of D prime. This implies that D prime divides D. And we're done. Any other divisor must divide D because it is the biggest of them all. So D equals the largest divisor. Because any other divisor goes into it. Okay, so that's a pretty weird proof. That's a heavy proof. It's cool. It's kind of amazing. Let's talk about a little bit of the repercussions of this thing. Do you feel algebra, do you feel that we're like headed to a new neighborhood? Yeah, it's a little heavier, right? It's a little like, oh, the buildings are getting weird. They're gonna get weirder. But that's exciting. I hope that excites you. We're finally leaving Kansas. It's great. All right, so, let's see, where did I want to go? let me just make sure I didn't miss any cool things that I wanted to say about this. Oh, yeah. How to find the S and the T. So, we now know that if D equals the GCD of two integers A and B, then D is equal to some multiple of A plus some multiple of B. And we don't know what S and T are for some integers. Trying to find those integers just cold is like, what the hell? You just end up like, you might as well get an Excel spreadsheet out, right? And like just have it print off. Get a code, write some Python code to try every possible thing you can think of and have it grab it when it's right. Well, that sounds shitty. So let me show you how to do this. It's all from the division algorithm. To identify S and T, use the division algorithm and be clever then. Be clever then. That's very vague. So let me show you what I mean by that. We're going to kind of recoil the division algorithm. So let's go back to our buddy that we already did, those two big ass numbers. They were, yeah. So recall that the GCD of, well, actually, let's go back to that computation where we had to find the GCD of 101, 400 and 994, 500. And so that process looked like this. Let me just put it back up on the board for you. We took this guy, and you need to have this all written out. You'll see why. It was 9 times 101, 400, plus 81, 900. And then this was 101, 400 equals 1 times 81, 900. We're almost done. 81, 900 equals 4 times 1950, 19500 plus 3900. And then this guy was our GCD because the next step was that perfect division. So what we do is recoil this toward the top. So notice that I've got 3,900 equals 81,900 minus 4 times 19,500. So I'm taking that last equation, that GCD right here, and I'm rewriting this and getting everything to the other side, because I want to put GCD equals some linear combination of that and that. And what I have to do now is keep kind of recursively unloading these things until I get back to those original numbers. So my pin is to get back to everything needs to be expressed in terms of these two. So I go to this guy right here. Let's see, 81,900. So check this out. 81,900 is 994,500 minus 9 of these dudes. So this thing right here is equal to 994,500 minus 9 times 101,400. So that's this thing right here. I'll try to keep these organized. And then the 19,500, I gotta do a little extra work on that. So let's see, so we got minus 4 times. 19,500 is that minus that, which gets me close. At least this guy's one of my numbers. So this is 101,400 minus 1 times 81,900. Let me stop for a second, just so you see what I'm doing. so that's the 19,500 right there. We're gonna wrap this. This will be it for today. We're just gonna get this sucker done and call it. Does everybody see what's up? Or any questions? Definitely make sure you're following, because it's simple, but if you don't see what's happening, it can get very confusing. The last move I'm gonna make is I'm gonna rewrite. Remember how I took 81,900 and did it here? I'm gonna do it again. And then that'll get me back to a linear combination of just these dudes. So we've got 494,500 minus 9 times 101,400. And I don't even need parentheses around that. Minus 4 times 101,400. I want to leave that because that's one of my key numbers. But I'm going to replace 81,900 with 994,500 minus 9 of these 101 dudes. And there's multiple nestings here, so you gotta just be careful. Keep those parentheses straight. And then when I do this, I'm just looking for all the multiples of each of these. So I've got 494,500. How many multiples of that do I have? I've got 1 minus 4. Wait, what the fuck is this?
994.
Thank you. Oh, that's supposed to be 994. Thank you. Okay. So, thanks, Greg. So I've got one of those, 1 minus plus 4 of them, so plus 5 of those guys. And then plus, let's see what we got for the 101,400 dudes. We got minus 9 plus minus 36 of them. So minus 35 of those, is that right? Check me out. Oh wait, no, I got more than that, yeah. How many you got? Minus 9, minus 13, and then plus then also minus 36, right? Because that 4, it's that minus. I better keep track here. Okay.
Is that minus 45?
Yes, I think that's right. Yeah, that sounds right, because I remember doing this before class. It's pretty painful. That's the kind of shit you do not guess. Like, no, I'm not doing it. So could somebody actually just check us out on that really quick with the calculator to see that that worked out?
What was the goal we were supposed to be getting?
We should get 3,900.
Typed it wrong or something.
Yeah, let's check. I'll check on my multiples and stuff here. So let's see. So we had minus 9, minus 4, and then minus 36.
You said 409,500 is what we want.
Say that again.
409,500 is that?
409.
I thought he wanted 3,900.
So we're,
3,900. Yes, sorry, that's what we should get. You got it? Wait.
no.
So I think this is wrong here, because I've got minus 9 of those, minus another 4, so that's these. And then I've got minus 4,
Yeah, it used to be minus 49.
minus 49, yeah. Let's try that.
That gets you 39.
They get you? Sweet, sweet. That's so cool. That's just crazy. I don't know, I like building that kind of stuff. I think that's fun. And it's not gonna make sense to you until you do it, and you'll get a chance to do it, I promise. No problem. I'll give you several to do, but not till Wednesday.
So like S would be 5, and t would be negative 49.
Yes, correct, yeah. Pretty cool. I don't know how you would like code that. I don't know if that's like, sounds interesting. No?
Pass.
Yes?
Pass.
Pass. ChatGPT, how do I do this? Give me the code.
It wouldn't know.
You really find it's pretty not helpful?
Depends on the language.
Like Python though, it can kind of kick ass on Python, right?
It can't do, it can do simple stuff really well. If you start getting any more complicated or you ask it to refactor anything or like look over your code and then it starts changing stuff,
Doesn't
it
know
gets
what the
kind
hell
of
going
stupid.
on.
It
So
doesn't
there's
know
still a
what-
job for coders in the world, there's still a job for humanity. Yeah.
Well, to be fair, those simple things that it can't solve, there are jobs for that.
Okay, cool, fair enough, yeah, that sounds right. All right, friends, that's it for today. We'll like pick this back up on Wednesday, and we are pushing this forward into our first algebraic structure that's not of your experience so far. Yeah. Are these like Regis owned? They seem like it. Like that all looks very Regis-y over there.
Oh, that's where the priest used to live.
Oh, is it?
That building?
Oh,
Like that little house, yeah.
Oh,
that's
who
where all the
lives there
priests
now?
live. Now it's a retreat house, so we just will use it. Yeah, before they built that new little house over there, that's technically, I don't know if
Oh,
Regis
okay.
anymore, but.
good Regis history. Thank you. Look at this guy. Have fun.
Those missing posters, we'll see if anyone's looking.
Yeah, exactly.
I was laughing earlier, because I remember, you, on back on the quad, I was writing the like, declaration of board life. And you were like telling me what to do, so that was my only experience doing it.
Nice, see, I'll
So
see
that's
you.
why I was giggling. If you
Oh,
saw me.
it's all good. Honestly, you giggling is great. I hope people are laughing.
It was really good.
Really?
Cause you're like, I don't wanna be the one to write it. I was like, I got you, I
I'm gonna
got
try to
you.
like maintain some kind of rapport. I feel like I'm gonna be told I need to clear the way. Man, you too. I'll see you on Wednesday.
Have a good day.
Yeah, you too. Bye.
Maybe. My name's Christian. David. I'm sure I have, yeah.
Were you gonna use classroom last week?
Yep, yeah.
That's when it was then. Could have been. This is your professor, huh?
Yeah.
I was trying to get my plant away that's in the hall.
Oh God! That was your
That's
plan?
my
Are
plant. Been there 2 years, sir.
you serious?
I'm dead serious.
We founded a home. I hope that's okay.
No, I got it from him. I said, that's my plant.
I'm so sorry. I thought it was okay.
No, it's just like we
Oh
have.
my God! It's not his fault. It's my fault.
It's been there 2 years.
And then for the first time, some bastard actually took it. Yeah.
I'm like,
Okay.
he was walking out with it. I'm like, what are you doing with my plant?
Oh,
It's like the
yeah,
professor
it's
gave
not
it
his
to
fault.
us.
Yeah, I did. I'm sorry. I didn't even realize this was an office. I thought this went straight through to the other
No,
side.
that's my office.
Okay, apologies. Sincere apologies. I'll bring you a plan.
Oh, I don't need any more things. I've had like 4 plants right inside there, but they just don't do it. So I put them out here and they,
Oh, my
between
God.
artificial and natural.
Poor
they
Cormac.
somewhat.
He must have been humiliated.
I'll have to get him a plant is what I'll have to do.
No, I got
He's
it.
like,
I'm the cause of all the trouble, so.
what class is this?
Abstract algebra.
Abstract, so I don't even know concrete algebra, let alone abstract.
It's, yeah, it's like before I heard all of that. It's good stuff. Yeah. For people like Christian who are going to grad school and that. Yeah.
Really?
Gonna try to, for sure.
Going to.
Yeah.
I'm trying to figure out where I'm going from, but.
I'm sure we've met before. This is my
Well, I
third
teach
year.
I teach doctors with PTO2 pharmacy and nursing, so.
Okay.
I apologize.
Good thing I was here, huh? David.
Nice to meet you.
See, there's my name.
Yes, I see now. Yes. How embarrassing.
No.
Oh my God.